This is the final part of the chain rule section, and it's the chain rule using Leibniz notation. So earlier we talked about there's Leibniz notation and Newton notation, and I personally feel that Leibniz approach to calculus is more of what we use. So just things to consider. We have our ways of writing this: h of x equals f of g of x, where u is g of x and y is h of x, which is g of u. We can come up with our expressions here for the derivatives using the chain rule. But under Leibniz notation, it's this dy dx is dy du times du dx. So we kind of did that in the last part of this section. But this is just to give you a formal idea that this is what Leibniz notation would look like. So in this example here, we have find the derivative of y equals x over 3x plus 2 to the fifth power. So we can identify that y equals u to the fifth power, and that u equals x over 3x plus 2. So a dy dx would be looking at the derivative of the y with respect to u. And so in that, we're going to see that as 5 times something to the fourth power. And that something to the fourth power is what u is. So that's our x over 3x plus 2. Now this is the u. And then times the derivative of u. And so this next part is my u prime, or du dx. And that's going to be low d high. So low is 3x plus 2. D high is 1. The derivative of the numerator is 1. Minus high, which is the x, times d low, which is the 3. All divided by the 3x plus 2 squared. I guess I should have realized this is going to be a much longer expression. So we're going to call that our du dx, which is our u prime. And so there's a little bit of cleanup that can go along with this. And we have dy dx equals 5 times x over 3x plus 2 to the fourth power times, and that's a 3x plus 2 minus 3x all over 3x plus 2 squared. So from here, these 3x's will go away, and we have this 5 times the 2. And in the numerator, we have this x to the fourth. So, and I kind of want to combine this 3x plus 2 to the fourth down here with the 3x plus 2 squared. So up top, we have a 5x, no, not 5, it's 10 because there's the 2. So 10x to the fourth. And down below, we'd have this 3x plus 2 to the sixth power. And again, that is the squared, 3x plus 2 squared, and the 3x plus 2 to the fourth. Okay. Let's look at another one. So we have y equals tangent of 4x squared minus 3x plus 1. And in this, the y could be considered a tangent of u. And our u would be considered the 4x squared minus 3x plus 1. So if we're looking for dy dx, we'd be looking at the derivative of the tangent, which is going to be the secant squared of u, which in this case is 4x squared minus 3x plus 1, so that this part is the u, times the du dx, which is u prime. That's going to be this 4 times 2x minus 3. So it doesn't do much on the cleanup part of this. Pretty much all we're going to get is 8x minus 3 times secant squared of 4x squared minus 3x plus 1. Okay. Let's see what's next here. Use Leibniz notation to find the derivative of y equals cosine of x cubed. So this notation is important. There's an x cubed and there's cosine of that. So our y would be a cosine of u, and the u would be x cubed. So dy dx would look at the derivative of cosine, which is going to be negative sine of whatever u is. Well, u is x cubed. Again, that's a u. Times the derivative of the u. So we want the du dx, which is also called u prime. That's going to be 3x squared. That could be left as it is. If you want to change around a little bit, you could say dy dx equals negative 3x squared times sine of x cubed. That's it. And we're done with that section. So yay, moving on now.